All right, thank you so much, Angie, and it's a great privilege to be here talking about this work with all of you. Turns out that I actually had this weird situation where I presented this work at a conference, so people who are not at Dartmouth kind of know more about it. Not a bad thing. So I'm excited about this presentation. I can promise you that I will not be able to do justice to this work in the next 15-20 minutes, but my hope is that I will provide enough of a teaser, enough of excitement about this, both from the sort of graveness of the problem we are facing, but also the potential for opportunities to do something here, right? So I want to kind of balance those two things in the next 15-20 minutes. I want to take some time to acknowledge everybody who has been a really important part of this endeavor over the last year and a half, something like that. So I want to say that this was developed, a lot of these ideas were developed in collaboration with Professor Stephen Peterson at Thayer, Victoria Holt, who is the director of the Dickey Center for International Understanding, Amy Newcomb, Noah Nicholson, Anais Boucher-Browning, all of them are folks from the Dickey side. They all helped in various parts of this project over the last year and a half or so. And as Angie mentioned, a large majority of the funding came from Irving, so thank you, as well as some support from Dickey. And a big shout out to a particular day, sometime in April or May, actually, 2023, where somebody invited me to this really curious sounding idea of something called Powering Peace. And I said, oh, what the heck, I'm free that day. Let me go and check out what's going on with these folks, right? So that's how it all started, right? So I knew possibly less than every single one of you in this room 2 years ago about this topic. And now I know a few things, so that's exciting. And by far the most important, I want to acknowledge my co-authors. Some of them are here. So Lily Yang, who is the main PhD student working on this, along with Sichi Ke, who is another PhD student, who unfortunately is not here right now. And Ryan, who is an undergrad student, soon to start his graduate work at Dartmouth. So those are the people who do all this actual work. I am here to present it. So there are 4 things here. I will not talk about the 4th part. I just want to tell you that that exists and there is some interesting work in that area that we've done. But I want to focus on the background, which is primarily the challenge, just trying to spend a few minutes talking about the enormity of the challenge that we are facing in this area. And then I'll talk about brighter things, such as the opportunities for energy transition. And then I will give you a little bit of a flavor of the actual work that we do. So the actual work is primarily in this 3rd part here and 4th part, which I'll not talk about. So much more here than what I can possibly talk about in the next 10 minutes. So more than happy, delighted to talk more about that later. So let's start with the background. And so as many of you may or may not know, there are some very serious challenges going on with respect to access to electricity in many parts of the world. Especially if you look at the number of people who live in these areas, this is a very big challenge. Of the 685 million people without electricity, some more than 60% of them live in these places called fragile states, which I will talk about at length today. There's a lot of attributes, a lot of characteristics that describe these places. Some of the important ones are weak governance structures, political instability, cycles of conflict. Cycles is important. This has been going on in many places for years and years and decades. Economic fragility, problems with infrastructure, not just electricity, but all kinds of infrastructure, unemployment, and then climate change vulnerability. For example, you see a picture here from one of these places where it's very dry, arid conditions. You see UN peacekeeping forces on the left-hand side there in one of these places. You see some description of, you cannot read this, but it talks about all these dots are various kinds of conflicts like battles and remote violence and violence against civilians and things like that. Lots of problems. Obviously, financing anything in this situation is very hard, especially if it's for something like electricity or energy infrastructure. This is very difficult, whether you're seeking funding from private or public sources. And then here is a really sad trade-off, paradox, I'm sorry. Many of these places actually have petroleum deposits. But what they end up doing is, since they do not have refineries, they would ship this out to some other place in the world and then import back in the refined products and then run almost the entire energy system based on that. Right? That's how a lot of these places work. And there is either little or no national grid in most of these places. And I keep saying most of these places, I'll be more specific in the next few minutes, but they don't have that, which means that people like this gentleman here, they have to work on more decentralized ways of accessing electricity, if at all possible. And it requires a lot of coordination between different stakeholders, which I will talk about depending on time available. So where does this put us in terms of the security side of this? Because the title here has to do with fragile states, right? So what's the connection between energy and security? So far, I've just said there are energy problems, there are security problems. What's the connection? So fuel convoys is the main connection between the two. Here is a prime example of that. For example, this place here, this is Juba in South Sudan, and this is about 150 miles away from the southern border of South Sudan, which borders with Uganda. And almost entirely the only way to get any fuel into this country and to run this city is through this 150-mile highway that goes from Uganda to South Sudan, to Juba, which is the largest city and capital city of South Sudan. And like it says here, the diesel travels through South Sudan. Corruption, armed checkpoints, theft lead to diminished supply and quality, raising prices, and ultimately limiting access to energy and electricity. Here is a staggering number. More than 50% of the UN peacekeeper fatalities happen because they're trying to protect the fuel convoys, right? It's a really big deal. And then there are lots of problems with, diesel generators. We know they're bad for the environment, bad for the climate change, bad in terms of, because these are old equipment, bad with breakdowns. There are clear fuel shortages whenever something happens with the security side of things. So in summary, there is a large amount of conflict, and a lot of it is affiliated with the whole process of fuel imports, right? So the idea here is, what if we can actually somehow find a way to bypass the dependence on this particular flow of fuel, in this example coming from Uganda to South Sudan, but this situation exists to a variety of extents in many other countries as well. So what can we do here? Let's think about electricity. So in many of these conflict-affected regions, there is almost no access to electrical grid, and things are not particularly getting better as we stand here and sit here and think about this. Less than 4% of the $500 billion per year in global renewable energy investments are apparently going to any of these 34 least electrified countries. So that's a problem. Now let's get down to the specifics. So the countries that I do want to talk about today are particularly these 5. They were chosen in after lots of deliberation with people in many parts of United Nations and lots of people on the DIGI side of things. These are the countries that are facing all of these challenges, and they are the places where there is or there has very recently been a UN peacekeeping mission that is functioning somewhat well. Let's look at this number. So this here shows how much energy is consumed as per 2021 in the United States per person. It's about 77,000 kilometers. Look at these numbers. This is Mali, South Sudan, Democratic Republic of Congo, Central African Republic, and Somalia. You see a negligible fraction of that consumed in these countries, right? So clearly, we can make an argument that maybe we should try to consume less, but there is a very strong argument that these countries need to have access to electricity, to basic things such as running a fan, having a light, so that when the sun sets, you still have some way of knowing what's going on and have charging their mobile phones and things like that. So what is happening in these places in parallel to these energy challenges is that we have a lot of UN peacekeeping infrastructure. So these troops are placed there with the aim to stabilize the fragile regions. And what they do is things like infrastructure investment, political agreements, security guarantees. There's lots of troops and personnel. They require electricity in various remote locations. So what they do is they run diesel generators, right? So UN compounds account for a large portion of the overall national electricity usage. Think about this for a moment, right? When I heard this, I couldn't believe it. I thought I misheard it. But something like 20 to 50% of the entire electricity consumed in the country is by this handful of little dots in the country, right? Like, 10 little compounds, each with a few hundred people. They consume about up to half of the entire electricity consumed by these places which have millions of human beings, right? So there is this huge contrast between those who have some electricity access and those who have none. But on the bright side, this also creates an opportunity to leverage on this ability of the United Nations to purchase power in these places. All right. So I still have time to talk about happier things. So lots of challenges. You're all you're presumably quite depressed at this time. So let me show you some good things, right? So one good thing is solar potential. These places have great availability of solar power. I'm giving you some examples here: Central African Republic, South Sudan, Somalia, three particular places that we focused on in this research. You see this availability of solar to be pretty high in all of these places. What about wind? Yeah, it's a little bit of a mixed bag. Somalia has some wind, the others have less so, but nevertheless, overall, there is a tremendous potential in terms of generating more than enough energy that you would need to serve all the population needs in these areas. So in theory, we're going to have a path forward, right? So what are the practical challenges to bring this theoretical idea to practice? First of all, it's not clear that we know what the different parties are thinking. So who are the parties here? So we have folks like the various United Nations agencies, and UN is big. Different departments within UN don't necessarily know what the other departments are wanting or doing, right? But then UN is a tiny part of this. There's the local governments, there's the national governments, there is various other powerful organizations, let's say, with a variety of degrees of military abilities and combat potential. There is the local community, the people who are trying to make ends meet on an ongoing basis. And then, if we want to make any difference here, we need to put in some money to purchase the equipment for solar, wind, batteries, etc., which means we have to talk about the private investors. And so, as a group, what are these various people thinking? They're probably thinking about these. I say probably because we have talked to a lot of them. So I think what they're thinking about can be summarized as these four main objectives. There is a lot of interest in reducing reliance on diesel. And yes, some people really care about environment. Others really purely care about the security angle of this. Either way, they care about reducing reliance on diesel. They want to minimize upfront cost because getting in large investments, millions of dollars into green renewable energy infrastructure in these places with high degree of uncertainty about everything, it's hard. So you do not want to take the challenge of generating enough capital upfront as a easy thing, right? That's a big deal. And then you want to have as reliable an infrastructure as you can provide. You know that renewables have some challenges with uncertainty of supply between day and night and between different seasons and so on. And then you want to provide electricity to as much of the local community as possible. Keep in mind that currently most of them have no electricity in the sense that there is no infrastructure, right? And then those who have it have a low reliability of the available electricity. So the good news is that in this conference that happened up campus at Dartmouth Hall there 2 years ago, actually, we were able to get in lots of folks from several UN departments, some entrepreneurs, including some of our alumni that are there working boots on the ground in these countries in various industry sectors. We got some folks from the international organizations like IMF and World Bank. We got folks from the private investment community, and so on. And there was a very vibrant discussion. What I learned there is that almost everybody wants similar things, but they don't want exactly the same things, right? Both are important. They are generally speaking similarly aligned, but when it comes down to the details, they disagree quite a bit. And one thing that came out of this is that there is a lack of a common language and a common understanding and a common tool for quantifying the key trade-offs. So that's what we set out to do. Good news so far. So now I want to talk about what we actually did, but just as a summary, the good news so far is that renewable energy is widely available and already highly affordable if you can put in the upfront investment and you can sustain that for a long period of time. So there's a lot of hope. So what we did, right? We started thinking about this as an optimization problem. And all along, we focused all along on these variety of objectives. So yes, we want to transition to renewables, but security matters, but upfront cost limitations matter, reliability matters, access to electricity matters. So looking at all these objectives, it's going to be a multi-objective optimization problem, and we have to make some assumptions. And one of the scarcest things to come by here is data, right? We have almost no public data set that we can just go to and grab a bunch of numbers and then crunch them, right? So there was a ton of effort needed in connecting with stakeholders and reading reports and like collecting all this information. And that's what a lot of this time of the students was spent doing. So for example, we were able to calculate some numbers and get a sense of the electricity demand. We're going to focus on PV panels, wind turbines, diesel generators, because whether you like it or not, they are part of the solution, and then storage batteries. And when it comes to renewables, we need to keep in mind that there is going to be a lot of fluctuations, both in the short run as well as in the long run, because of various sources of uncertainty, and we need to account for them. And and then about transmission cost, we need to make some assumptions depending on the geography of where these places are located. So let's jump into a little bit of an overview of the technical work that we did. So the goal here is to design a hybrid renewable energy system. And we are going to focus on all those 4 objectives. And those of you who care about this, I would like to say that this is a problem that belongs to the category of stochastic programming problems with multiple objectives. So you already know. What stochastic programming means is that you divide the world into two points in time, okay? One is what I call here and now. So here and now, I need to decide how much I want to invest in various equipment. How much do I want to invest in solar panels? How much do I want to invest in wind, in batteries? And maybe I want to buy or phase out some diesel generators, right? So that's the decision I have to make now. And then later on, we have to wait and watch and figure out how we want to run this system. And how we run this system depends on the actual conditions at that time, which, I don't even know it's going to rain tonight or not, right? So there is a lot of uncertainty. We cannot possibly know what's happening in Central African Republic on 16th of May in 2 years from now, right? So there's a lot of uncertainty we have to deal with. So what stochastic programming does is that it divides the world into these 2 steps. So it supports the long-term tactical decisions, and then it accounts for the short-term decisions related to how you want to do things on an hourly dispatch scheduling side of things. And people who are more knowledgeable than me in this room, like Erin and many others, will tell you that this is as important or even more important than making these decisions, because if you forget this, then this might go horribly wrong. So there's a lot of complicated mathematics here. The specific things we do in the first stage is we try to decide what's the right amount of capacity to install for each technology and what's the fraction of electricity demand for the local community that we want to serve. Keep in mind that I would love to serve everybody, but that may or may not be the right thing to do. That's one of the objectives. I would like to serve everybody is one of the 4 objectives that we have, right? So we decide those things in the first stage, and then on the day of operations, we're going to decide renewable energy availability and then hourly dispatch schedule. So getting slightly geekier, so there is this method called epsilon constraints method, and it finds out something called Pareto optimal solutions. This is important. So what we are saying here is we do not want to go to decision makers and say, yeah, Georg, I understand you have this trade-off going on. I will tell you what's right for you. You just do this, trust my math, right? We do not do that. What we do is we will go to people and say, look, here is the various possible things you can physically do. And I can assure you that all of these are potentially good candidates. You have to make the decision. I can tell you that there are no other good candidates. What does it mean by good candidates? A good candidate is one where you cannot improve one objective without worsening another, right? As long as that's true, it's a good candidate, then it comes down to your preferences for what you want to choose among various good candidates. And that's the trade-off decision that you make. So what are the objectives? Remember, these are the objectives. We want to minimize upfront cost, minimize reliance on diesel. We want to serve as much of the community as possible and minimize blackouts, maximize reliability. Oh, sorry. This is where I say that there's lots of work people did. This is that slide that says there's much more to it than I'm saying. But really, we just want to hide that and just highlight that there are things that are pretty common sense. The amount of electricity that flows in equals the one that flows out. There are constraints, physical constraints on how panels, PV panels, wind turbines, generators, batteries work. So all those are embedded in that math. This table was a lot of hard work. Getting these kinds of numbers was a project in and by itself. So I just want to give a shout out to all the hard work. This is not fun work. Like, where does that number come from? Nobody came to do their PhD or master's to find out where that number came from. You don't have to do all that if you want to get anywhere, right? Oops, sorry. Maybe some people did, I don't know. All right, so let's focus on this. This is my second last slide, and then there is a thank you slide after those, right? So I'm almost done. What is this? There is 4 pictures. Every one of them shows on the x-axis the upfront cost. On the y-axis, it shows the power generated by diesel, right? Both of these are bad things. We want as little upfront cost as possible, as little reliance on diesel as possible. So your ideal point is here, 0,0, right? But we don't get that. What we get is these various trade-off curves. And the question is, where do you want to be on these trade-off curves? I don't know. It's something that the decision makers can decide, but at least they look reasonable. They make sense, and they hopefully communicate in a simple visual way to somebody who has been thinking about this problem out there to see what are their options really. What can they pick from? There are multiple lines here, and there's like this 2 by 2. So I'm kind of showing in a variety of different ways. And what I'm parameterizing these is based on how much of the local community gets served and what's the reliability level we are looking for. Remember, this is quite different from what the kinds of research that happens for the developed country context, where I have here a data point where I say, well, what if I only provide a system that's 65% reliable? Anybody here who is happy with an electrical grid that 2/3 of the time you get electricity? Not too bad, right? No, it's horrible. I know that, but the sad reality is that as compared to not having any electricity at all, it might be a pretty good situation. So these are the hard trade-offs we have to look at. And then my last slide, that is to say that this stuff actually led to some really cool insights in terms of how to build the math and algorithms. And I will give you one of them in the next 2 minutes, and then I will be done. Here's an example of what you would get if you rely on just the existing literature on how to do these things. That thing over there. What it is saying is that, remember that 2-step, right? We have to decide what to do now and what to do later. And what to do later is dependent on exactly what transpires on that day, right? So you have to look at a few possibilities. And the question I'm asking is, how many possibilities should you look at? How many is good enough, right? We call them scenarios, right? Ideally, if you look at very few possibilities, this is the only slide I wanted Klaus to be not there on, but sorry. Okay, let me get this right.
Finish up right now.
Thank you.
I can leave again if you want.
So how many scenarios is really important, because if you do too few, your model runs quickly. That's great, but it might give you inaccurate results, right? If you do too many, you're covering everything, which is great, but then it can take forever to run. So here is a trade-off. When we used 1900 scenarios versus when we used 15 scenarios, this is state of the art here, right? And I don't know this literature well enough. So when I looked at it, I thought, that's interesting. And we said, like, okay, let's see how good the 15 scenario version is. It turns out that if you calculate everything based on 15 scenarios, it runs very, very quickly, like nearly 0 minutes. And it, by the way, creates an illusion that you can fully eliminate diesel, when in reality, you have approximately 20% reliance on diesel. That's hidden. That's not even visible. The math models will do it and will feel very happy and then go to the practitioners and then realize that it's all horribly gone wrong, right? So there is, all I'm saying in this slide is that there is lots of great OR, operations research work, math and algorithmic work that was also exciting. And these are the kinds of conclusions we can draw. just for you to look at them. Thank you very much.
Questions for Vikrant?
What I missed, Vikrant, was regionalized or localized differentiation, because the boundary conditions on the African continent vary.
Yeah.
Climatological regions, morphological, hydrological, etc., etc. Could you
Great.
comment?
Yes, absolutely. So, for example, this one I showed you is about a particular compound in this place called Baidoa in Somalia. On the other hand, a lot of the other work we did was for another compound, which is in Bangui in Central African Republic, and 100% right. The meteorological conditions are different, the economics are different, the security situation is different, the geography, because where do you put this thing?
You did take care of
It's all
that.
case by case.
Thank you. Thank you very much.
I'm subbing in for Klaus because he wasn't here the whole time. So, you have that great results. First of all, great presentation and work. Really good job, Lee. You have that result that when you sample more uncertainty in scenarios,
Yeah.
you reveal myopia.
Yeah.
But when I look, I'm sorry to nitpick at that table that you just showed. Like, how do you know that you've sampled enough uncertainty? And
Good.
yeah, I'll stop there.
Perfect. So my assumption here is that what is going to happen, we are looking at 10-year horizon, by the way, because people said 20 years is crazy. Nobody knows what's happening in some of these places in 2 years from now, right? So 10, 5, that's the kind of horizon we are looking at. That's something I didn't mention. However, what I'm assuming here, there's one big assumption I'm making. I'm assuming that everything that happened in the last 20 years, so 20 multiplied by 365, 7,000 something days, is everything that can possibly happen in the next 5 years, right? You can all judge that assumption, how you feel about that, but that's the assumption under which this is the true numbers. Good question. Yeah.
Sam is here. Sam is working on a really nice project with her idea where you can actually try to find out the subspace of parameters where things go bad. And then you can sample more in that area to get the boundary between things go bad and not. And that's standard arbitrage because people who build a turbine engine blades do that because they are concerned about failure.
Yeah.
So that might be a way to use the 1900 much more smarter. It's not finished yet, the paper, but I think that would be a nice way to enhance that.
Yeah, no, absolutely. I think what you are saying is that scenario reduction is a huge topic, right?
Yes.
And what we are assuming here is all that matters is average case.
Yeah.
Stochastic programming, the vanilla basic stochastic programming assumes averages is all that we care about, but there is, like Klaus said, there is much more to it. You might want to focus on areas where things can go particularly bad, 100%. Yeah. And one last sentence, this 15, this is just a k-means clustering that people do. And they just take that and say, all right, this is it. This is the reality I'm going to assume. I'm simply saying that's actually pretty problematic. We need to do better. But comment, absolutely.
And I'm going to cut Vikrant short
Yeah.
a little bit. We're going to say thank you to
All right.
you.
Thank you.
Vikrant, just because we have the other group coming in really quickly. So thank you everybody again for coming.
So I had